Hello everyone, welcome again in online tutorial about support vector machine linear classifier. Today we will have a tutorial about how to make a linear classifier because we have actually not only linear but also non-linear. But today we will constrain our discussion only for not only for linear classifier. Uh, the the uh, the idea is that in artificial intelligence kinds of method is as compared to the mathematical modeling is that we don't have models here. We have to build our own models in by inputting some features. It can be product features, can be process features, can be anything. Input data from our topics, put into black box model, and this black box model will create our own equation. It is not depend on a certain types of equation or model, but it is free. And the output should be some kind like dependent variables that can be classification about a good and bad, and then yes or no, or maybe acceptable or non-acceptable. Okay, let's see from in our discussion today that we have some kind like a figure in front of our screen. We have a figure about classification. The black dot signifies the plus values. It is called a positive classification, and negative classification. It is a white dot that is signified by equation wx plus b less than 0. What is wx plus b less than 0? It is some kind like constraint that if any of our features multiplied by a certain value of weights and plus the bias, if it is less than 0, then it can be classified as a negative values or -1. Uh, on the contrary, if wx plus b higher than 0, it can be plus 1 or positive value. Okay, this black box model here, we have some kind of equation that function x comma w comma b equal to signomial value of wx plus b. So the question is that how would we classify this data? Okay, let's see from our figure that we have now classification lines here. In the upper part is this positive classification and negative classification in the lower part, and we have three lines all together in parallel. That the goal is that how to make the how to compose or maybe construct the equation of this classifier or a line classifier by minimizing the dot products of weights, the transpose of weight times weight, subject to a constraint. This constraint is some kind like represent the classifier lines, where if it is y times wx plus b, if it is higher, it should be higher than or equal to +1. So you can get further about this topic from our classroom activities. So now we are trying to model this kind of classification into our Python, and I think you have already installed your software, and if you have installed the software properly, and then you can get this kind of you can go to Anaconda tree, or maybe you have a tool, and you can press the spider. It will goes to this kind of screen, a blank screen of Anaconda. So first of all, before continuing to model further about the classifier, we have to import some library. For instance, we have to import NumPy or numerical Python as NP. The NP or SP or NU, it is whatever you can put any name as you like. And the second library is that the SciPy. The SciPy will contain some algorithm to solve any kind of optimization model. It can be linear, non-linear, can be any convex, non-convex, can be with constraint or without constraint. So from this problem, and then we have to not only import SciPy, but specifically we have to put another another uh, uh, another library inside the SciPy. We call it from SciPy. we have to import optimize. So we are focusing now to optimization. And now we are going to extract or to take data from a certain source. In this case, we have a source of data from our example. And please keep in mind that you have to put your example files inside a Spider Python 3 folder. Otherwise, Python will not be able to get the data. And in order to get the sample and put into the Python software, you have to follow this kind of syntax. For instance, path is to show which place you would like to take the data. And then we have Python and data and data file for class Excel. Is it correct? I don't know. Yeah. Python data file for class Excel exercise SVM. Oh, it's very long. Okay, class Excel exercise. What is exercise SVM classification? All right. Then CSV. Okay. This CSV, sorry, it's not should not be star, but should be something like this. Yeah, this one. CSV means comma separated values. This is another type of Excel, but it is stated as a text instead of numeric. And df, it is your data frame. So we can get from here, get from text, get from text, get from text because it is text. The path is text value. We have to replace the path into the text into numeric. So we here have delimiter. Delimiter means how to recognize the value is separated by comma or by semicolon. But here we have because CSV comma separated value. That's why this delimiter is a comma here. So it's comma, and then yeah. What else? Yeah, skip because we have header. We don't want to include header in computation, right? We have x1 to y. We have header, but we don't know what to include that one. So skip header in the row number 1, and then we have to fill in any values. If we recognize any values with for example NA or non, what is NA? I forgot what NA. Something like non-assigned, yeah, non-assigned value by a certain number, very low certain number, so that Python will exclude this from the computation. So the data type here we have data type is float because it is numeric. Then and we have to state which columns that we would like to include into computation, and therefore we have user columns from 0 to 7. 1, 2, 3, 4, 5, 6, 7, right? Okay, let's see. Column number 1, yeah, 1, 0, 1, 2, 3, 4, 5. Oh, sorry, it is from 6. Okay, from 6. Okay, 0. How many? 1, 2, 3, 4, 5, 6, 7. Yes. Then we have 7 column. Okay, here. And what else? Yeah. Now we have to define within the variable which one is the independent variable, which one the dependent variable. So here we have the x equal to data frame, and we have also we have to mention that the column from 0, sorry, it is to be here without space, from 0 to 6, it is the independent variables, and column data frame, and then comma number 7. Yeah, column number 7 is the dependent dependent variables. And what is this? Okay, so we have to put here time, and now we have to start our computation. Okay, let's say that we have put index I. So we have here for I the index of its feature, x I represent to x or feature of the independent variables. Okay, and then we have to define the function, the objective function. All right, and yes, okay, and therefore we have to return the values of the objective function equal to 0.5 times, oh, it's times, yeah, numpy, sum numpy, because we have now it is a dot product between w and itself, and then we have to return the values. All right. Oh no, it is already. Okay. Now we have defined our function for the objective. Now we have to define also the constraint of the objective. So we have here constraints. Constraint one. Oh, sorry, just constraint one, and then we have same variable. This is the weight. Then we have to zz, but you can take any. But I like to call it zz. Okay, zz equal to, yeah, yi. All right, times what is times? Okay, times numpy, and then dot product between xi times w, and then we have, okay, yi times numpy. Okay, and what else? And p dot, yeah, should be minus one. All right. And now the question is that where it come from? Let's say that half times the summation of dot product between w and w. We can check it from here. W transpose times w divided by 2. And we have also one constraint here. It is wx plus b should be less than 1. Sorry, offer than plus 1 times y. Here also yi dot product between xi and w, and it's minus 1. So it is a convention of the SciPy that in order to represent a constraint in the way that the SciPy would like to read, we have to shift all of this right hand side value into left hand side. So therefore we have here minus 1, and we have here 0, right? So this value, of course, there is no sign this over than or lower than, but the convention saying that if it is written like this, it will be equal to higher than something, higher than 0. So now you have to return the values of our constraint as zz. Okay, now we have, what is this? ZZ design but never be used. Yeah, okay. Let's forget about this, but it will be, yeah, finally it's missing, right? Okay, SciPy it is not. Okay. Now we have to put the first for the first iteration we have to guess one value for the weight. Okay, now we have put here for the first guess numpy dot zeros. Zeros mean the whole value in the matrix should be equal to 0. So it's 0 0 0 0. And the number of 0 is equal to the length of the x. So if we, for instance, we have here, how many? 1 2 3, yeah, we have 6x, means we have the 6 number of w. Okay, and we put here x 0 because it is something like for the first iteration. And okay, yes, now we have complete. And don't forget to put the result here, because we would like to investigate whether this the result, sorry, yeah, the result is really feasible or not. And now we have a result here. This will be optimized dot minimize. Yeah, because we would like to say that the optimization model is minimizing something, minimizing the objective function. Therefore, we have to put minimize here, and minimize, and then the bracket. We have to first put into the syntax about the function. Then this function is the objective function, and with the first case is w0 with the constraint is equal to uh, okay, we have function here, the function of the constraint, and yeah, okay, and it is equal to constraint one, comma, and we have also the type. We need to put here what is the type of the constraint. It is inequality of it is equality constraint. But here we have inequality constraint because we have sign is higher than or less than. But if the value is equal to, means it is to be equality constraint, right? So we have here type, it is equal to inequality constraint. And it should be using not using this kind of bracket. I think you should curly bracket. This to be fine. But okay, let's start doing the right way according to the guidance from NumPy and SciPy, which I have to curly bracket. And yeah, we have to put the option here, and the option saying that we need to put the display on screen. So the display should be yes or true. Okay, the display should be, but you don't have to remember all of this because you can get from the NumPy literature how to write this kind of syntax. This quite long. Even I'm not really remember how to write it. And yeah, we have put the result. There is no any error message here, and we can print the result. Right. Okay, now after we have print the result, we are now trying to get whether it is the correct procedure to have the weight values from the optimization model. Okay, let's say. Okay, now we have index error, index 7 out of bounds for axis 1 with size 7. So here we have seven dimension of the let's say how many dimensions? 1, 2, 3. We have 7 dimension. Yeah, exactly, it is 7 dimension. But sometimes if this kind of splitting between independent and dependent variables are not working, then you could use this alternative solution to find or to split the dependent variable and against dependent variables using df. Sorry, it is using df and then comma -1 and y equal to df comma -1. Okay, let's check this. Yes, I think it says that x, it is -1 is the last column in the of the data. So here it's mentioned that y is the last column and x is after the last column. It's -1. Okay, let's say now we can try to run this model. Yeah, now we can successfully produce the result. So the problem is that whether whether we are sure that the model is correct or not, now we could do the same for doing some kind of validation. And therefore, we have to split the data into two. It is maybe some values, some rows according to as a tester, and some rows as a trainer. So we have two types of table that we have to split a table into two, a table as a trainer and a table as a tester. And using this splitting, we can validate whether our problem is correctly solved or not. Okay, first of all, we have to again set the table and divide into two. In that case, we have two different table, trainer and and trainer and tester, and we have to randomly choose or pick again some numbers of rows from the table, how many rows for as a training and how many rows as a tester. Okay, now we can use this kind of syntax, numpy random and then shuffle and then df. All right, and we have two type of table now, training and testing and test, and we have to put id here, sdf. Okay, let's say we pick the first 100 randomly from the table as a training. So we can put the syntax 100 and then and we have here for testing. So after 100, so 101 and until the end of the rows. So we can put here 100. Sorry, we have here 100 comma and yes, put in again here. Okay. Okay, so now we have already if you want to check which rows as a trainer and which row as a tester, and then you can just print training just for checking. But of course it is not compulsory, but you can do training and test. Okay, and now we have to put some kind of like identification here. Which within the new tables, we have two new tables. Which one is the independent variable? Which one is independent variables? So we now create a new variables here, xa equal to training, because now we have a new ID. It is called training for table one, and so same procedure as we are doing this one, but it's not x, but it's using x. So it is xa equal to training. It is not anymore data frame, but it's to be training, and y, and it is training. All right. Yeah. It is for training, and we can create the same for the testing. Test the same way for test, and it should be xp and yp. Okay. Now we have already composed our split our tables, original table into two, x a and b, and in each of those tables we have also split into training and test, sorry, into x and y, dependent and independent variables. And now we of course you can print x a y a x b y y b, but I will skip at this point, because yeah, this is just for checking. It is the correct I mean division or not between training and test. Now we have to again to repeat the optimization stage. Just copy of this optimization stage or syntax, put in here. But keep in mind that it's not anymore x, but to be xa, right? So you have to change x with xa, y with y. All right. Yes, len xa. Okay. Uh, you can print the result, and but you can also skip the printing of the result. Otherwise, the most important thing is that you have to state that now you have new weight. It's not anymore weights that you state in the first model, but now you have the second weights, the set of weights that to be your new values of weights that you need to use as a variables, and to measure whether your models is really valid and credible. And therefore we have to put here the result as for x. So w2, it is some kind like the new weights from the new tables. And now you could again make a classification based on the result of your optimization here. So for instance, now we have I, right? For I, that x in enumerate of xp, now you have xp, right? So doing like this, okay, just put it set 3, it's fine. Set 3 has to, you can even divide and so on, but never repeat the previous variables. Now we have equal to, because here we have equation here, we would like to find y. Right now, we would like to find how much the value of y. The value of y determining by division of plus 1 divided by wx plus b. So y will be higher than that. So we can write here that set 3 equal to 1 divided by, but set 3 represents the y, but it is not the true, the real y. We will try to compare set 3 against the original y values in the table to make validation. So here we have numpy dot, yeah, dot product between xp x, sorry, dot product of xp xpi, all right, comma y y2, because now we have weights. So xp times the new weight that we have set as a new for the validation. And okay, the numpy should be here. We need one more. Okay. Now we have set 3 values. Okay, this is the important part. So if, okay, bracket, set 3 is yeah, higher than or equal to 1.0, then now we have new variables. We call it set 4. Set 4, it is just to transform from the original Z3 into the new values of y that can be matched with the original y in the table. So set 4 equal to 1.0, because set 3 can be 100, can be 1000, even can be 0 point something, and therefore you have to transform those values according to the logic that, for instance, if set 3 is higher than 1.0, then it should be positive side, or black dot, or and the white dot for each, for example, is less than or equal to -1. So here again we have also else if it is how Python is saying that, step, just to make simplification of the syntax. Step 3 is a less than, okay, yeah, less than or equal to -1. And we have, sorry, we have set 4, it is equal to -1.0, right? Okay, now we have set 5. What is set 5? The C5 equal to, sorry, it should be, okay, yeah, here is better. Yeah, okay. Z5, okay, to we would like because Z5 is the okay. I would like to put here some explanation. What is Z5? Z5 is a like error method. Error method. Okay, and Z4 sorry, Z3 is Z3 is uh, real real values of Y, and Z4 is not real but real values is the transformation of Z3. All right. Then we have C5 here. We have C5 is just it's nothing but the measure of the error, how much we deviate from the expected values. So here we have NumPy then sum because we would like to add all error of the entire of our training not training I mean testing rules, and therefore it should be Z4 minus YBI and okay, divided by the length of the test. All right. So now we have no error. Okay. Okay. Good. Then we can print the error is or the error value is okay, comma Z5. Yeah, because we need to make a percentage to have a percentage values of Z5. Therefore, Z5 should be times 100. Mm, all right. Okay. Let's check. What is this? Undefined name NumPy. Okay. Now we can because we have already NumPy state as NP. Therefore, we have to put here not NumPy but NP. NP. Yes. All right. Okay. Now we have the values of our test. Okay, let's start the model and to check whether we have already uh, meet the validation test here. Just press yes. We have zero error. Means each of single rows has been processed optimally by the support vector machine algorithm, and by using only 100 rows as a training rows, we can make validation without making any error. So I think this classifier is very strong and we can use for our application here. I don't know what is the value of x, y, 1, 2, 3 to 6, but using this set of data from our sample about 398, and we split it two. The first 100 as a training, and the rest of the data as a testing. So using those support vector machine classifier optimization, finally we can have zero error, which means our classifier is valid because we have test according to the original data. Okay, this is our today's tutorial, and welcome to the next tutorial about naive Bayes classification. And have a nice day. Thank you.